Have you ever actually stopped to think about why you don't just slip and slide uncontrollably when you're walking down the street? Or, why a bicycle eventually rolls to a complete stop the second you stop pedaling? Well, we live our entire lives totally dependent on, yet constantly battling, this invisible kinetic force. It's a fundamental law of physics that makes literally all of our controlled movement possible, but at the exact same time, it actively degrades basically every single machine we ever build. It's hiding right in plain sight, completely dictating the boundaries of our physical reality. Welcome to today's Explainer.
Okay, so here's our roadmap for today. We're going to start with the invisible force, then defining the mechanics, move into the 4 types of friction, explore how it's a double-edged sword, and finish up with the final recap. Let's jump right in.
Section 1. The invisible force, hiding in plain sight.
So, the direct answer to those everyday mysteries? It's friction. It's this omnipresent force that dictates exactly how we interact with the world around us. But to really get why it's so inescapable, we kind of have to zoom in. Because on a microscopic level, absolutely no surface is truly smooth. I mean, even a highly polished pane of glass looks like a jagged mountain range if you put it under a microscope. And when 2 of these jagged surfaces touch, all those microscopic peaks and valleys just interlock. Plus, the electromagnetic forces between the atoms of those 2 surfaces are actively attracting each other. This inescapable microscopic reality is exactly what generates that macro-level force we experience every single day.
Moving on to Section 2. Defining the mechanics, how it works.
All right, the crucial thing to remember here is that friction is fundamentally a force that consistently opposes motion. But it's so much more than just the physical act of rubbing 2 things together. In physics, you can think of friction as the kinetic cost of interaction. Whenever one object moves over another, this force acts in the absolute opposite direction of that movement. Mechanically speaking, your kinetic energy, that's the energy of movement, is actively being converted right into thermal energy, or heat. Basically, you're paying an energy tax just to move one surface across another.
And that perfectly illustrates why it's so profoundly important to us. Without this kinetic force aggressively opposing our motion, taking a simple step forward would send you endlessly gliding across the room with zero way to stop. Driving a car? That would turn into a completely uncontrollable, continuous slide the second you tap the gas. You wouldn't even be able to hold your phone or a coffee cup right now. It would just instantly slip right through your fingers. Friction is literally the invisible grip on our world, giving us absolute control over our physical environment.
Section 3. 4 types of friction, categorizing the force.
So physics actually breaks this kinetic cost down into 4 main categories. We've got static, sliding, rolling, and fluid friction. Let's break these down and see how each one dictates different mechanical interactions in our day-to-day lives. Let's start with static friction. This type acts like a powerful anchor, preventing an object from moving at all. Just picture a super heavy box sitting totally at rest on the floor. What's really fascinating here is that static friction is almost always the strongest of the 4 types. Since the object is just sitting there, those microscopic imperfections we talked about earlier have time to really deeply settle into one another. Sometimes the atoms actually bond, kind of cold welding together on a tiny scale. And that right there is exactly why it takes way more energy to initially get a heavy box moving than it does to keep it going once it's already sliding.
Now, once you push hard enough to overcome that powerful static anchor and break those micro welds, sliding friction takes over. This comes into play whenever 2 surfaces are actively sliding against each other. Because the object is already moving, all those microscopic peaks and valleys just don't have the time to fully interlock or cold weld anymore. So naturally, sliding friction is inherently weaker than static friction. But it definitely still creates a continuous grinding resistance, generating a ton of thermal energy or heat as those surface imperfections just constantly crash into each other.
By contrast, rolling friction fundamentally changes the whole mechanical equation. This is the specific force that acts on rolling objects, like the wheels on a car navigating a highway or a train rolling down a track. Rolling friction radically shrinks the contact patch between the 2 surfaces. So instead of dragging those microscopic imperfections directly across each other and grinding them down, a rolling object is basically continuously lifting and placing itself back onto the surface. This massive drop in kinetic resistance is exactly why the invention of the wheel was such a monumental, absolute game changer in human engineering.
And hey, we aren't just limited to solid surfaces here. Fluid friction kicks in whenever objects move through liquids or gases. You've experienced this yourself if you've ever pushed your way through water in a swimming pool or felt the air resistance buffeting your hand when you stick it out the window of a moving car. Honestly, overcoming fluid friction is one of the single most expensive challenges in modern science. Engineers literally spend billions of dollars combating this specific force, using cutting-edge aerodynamic designs in both aviation and cars, just desperately trying to slice through the air and water as efficiently as possible.
Section 4. A double-edged sword. The good and the bad. So friction really presents this fascinating, totally inescapable paradox. On one hand, it's the absolute hero of our daily lives. I mean, it grants us the vital traction we need just to walk down the street, it lets us safely and predictably hit the brakes in our cars, and gives us the mechanical grip to use our tools. But at the exact same time, it acts as a highly destructive force. It's the ultimate villain in engineering, relentlessly wearing down and destroying machine parts over time, producing all this unwanted, dangerous heat, and driving up global energy costs by constantly bleeding off valuable kinetic energy to entropy.
All right, bringing us to Section 5, the final recap, putting it all together.
To wrap up what we've thoroughly covered today, friction really is the ultimate regulator of motion in our universe. It inherently opposes movement, acting directly between surfaces that are in contact. Whether it's securely locking an object in place as static friction or resisting your forward momentum through sliding, rolling, or fluid states, it's this constant, unavoidable balancing act. A true tug-of-war between vital, life-saving utility and relentless mechanical wear and tear. Ultimately, grasping the intricate realities of this often misunderstood force is exactly what empowers us to push the boundaries of innovation. By deeply studying friction, we can actively engineer way better machines and design significantly safer vehicles. I mean, just look at modern maglev trains. They use incredibly powerful electromagnets to literally hover just above their tracks, completely eliminating sliding friction in the process. Innovations like that prove that mastering this force is absolutely the undisputed key to unlocking next-generation, high-efficiency technology.
At the end of the day, friction is the invisible toll we pay for moving through the universe. It's a fundamental tax on our kinetic energy. So, knowing exactly how much it dictates the very parameters of our world, how will you use or overcome friction tomorrow to help build a more efficient future? Thanks for joining me on this Explain.